this is going to be a tutorial class on what we have studied in the last few classes. What we have done in those classes, we have defined what is going to be the log mean temperature difference, what is a counterflow and a parallel flow heat exchanger, what's a double pipe heat exchanger, its advantages and disadvantages. And while calculating the log mean temperature difference, we understood that if there is mixed flow, that is a flow type which cannot be categorized either as purely parallel flow or purely counterflow, which in many situations, for example, whenever you have multiple tube passes in a shell and tube heat exchanger, or even in a double pipe heat exchanger, if the flow is across the tubes. So for all those cases which were somewhere in between the parallel flow and counterflow, which are collectively termed as mixed flow, a correction factor to LMTD has to be used. The correction factor is generally denoted by F, and so the LMTD for mixed flow would be F times the LMTD for counterflow. So the log mean temperature difference was derived, it came automatically as the correct mean to be used for the temperature difference between the inlet and the outlet. And we have also seen that if the temperature difference, the temperature of the change of the hot fluid and the temperature change of the cold fluid if the difference is not substantial, then arithmetic average can be substituted for LMTD. However, in order to maintain uniformity throughout our discussion, we will always use LMTD for all our calculations, because that's the correct average, logarithmic average, that's the correct average to be used for the temperature difference. We have also seen what a shell and tube heat exchanger will look like with multiple number of tubes, and in some cases there can be multiple shell passes as well. So there can be 1-2 heat exchanger, there is one shell pass, that is the shell fluid is going to flow through the shell only once, and 2 tube passes where there would be flow through the shell in the upper half and then flow through the tubes in the upper half of the shell, and then it changes its direction and flows back through the shell once again. So the tube side fluid enters the shell, leaves the shell, comes back to the shell and then leaves once again. So 1, 2, 2, 4 and similar such multi-pass heat exchangers are quite common, and whenever you have those kind of heat exchangers, the LMTD has to be corrected by the incorporation of the correction factor denoted by F, and this F is to be read from a graph which I have shown, that the value of F can be calculated, can be read from the graph where the two non-dimensional temperatures are defined, and as a function of those two non-dimensional temperatures, the value of F can be read from the graph which is provided in any textbook on heat transfer. So with that background, I think we are in a position right now to solve for some specific problems in this class, and then from next class we will go into purely shell and tube heat exchangers, their efficiency calculation and so on. But right now let's concentrate on the first problem, which is a double pipe heat exchanger. It's a thin walled double pipe heat exchanger. I have underlined the thin walled, these two words, so as to mean that this essentially means that the resistance to heat transfer by the wall of the pipe is negligible as compared to that of the inside convection coefficient and outside convection coefficient. I forgot to mention that we have also introduced the overall heat transfer coefficient U, which is just the algebraic sum of the resistances provided by the convection inside coefficient of the tube, the resistance of the thermal resistance, conduction resistance of the tube, and the resistance which is denoted by which is provided by the outside convection from the outside of the tube. So normally it's a sum, the 1 by U, which is the overall heat transfer coefficient, would be equals 1 by Hi plus 1 by HO. Hi and HO are the inside and the outside convection coefficients, and another term which is due to the resistance of conduction through the tube wall. To this we sometimes have to add the dirt factors, or the deposition on the inside as well as on the outside of the tube, which will provide additional resistance to heat transfer. So those dirt factors are to be they act as additional resistances, and they are to be added to this relation in order to obtain the overall heat transfer coefficient, which is denoted by capital U. So in this specific problem, it's a thin walled double pipe heat exchanger. So we do not need to consider the conduction resistance, and nothing has been mentioned about the dirt factors. So we'll assume that these are relatively new or just serviced, and therefore the heat transfer resistance due to these dirt factors, they do not exist. So it's going to be a sum of only two resistances. One is the inside convection coefficient and the other is the outside convection coefficient. So engine oil is to be cooled from a high temperature to a low temperature, and the coolant used is water. The flow rates of the, if you see the flow rates for each of them, that means for the oil as well as the water are provided to be 2 kg per second. The engine oil temperature is to be reduced from 160 to 60. The ID is 0.5 meter. The OD is unimportant, as we have mentioned it's thin walled. So had this not been the case, then the OD of the tube would have to be provided with the material specified, such that we can find out what is the conduction resistance of the pipe, but that is not relevant over here. It is also mentioned the overall heat transfer coefficient is 250 watt per meter square per Kelvin. What you need to find out is what is the length of the heat exchanger, length of the double pipe heat exchanger to be provided, so that this heat transfer process is possible. In order to do that, first we need to find out what are the properties, and the properties can be found from your textbook. So if I consider oil, the average temperature is the average of these two, and at that temperature the value of the specific heat can be read from the table in your text or will be provided. For the coolant water, we do not know what is the coolant. We do not know what's the mean temperature going to be. So we are going to assume an average Tm, average water temperature. Let's assume this to be 40 degrees centigrade. It's not going to matter much. You would see towards the end, and the coolant water is at 25 degrees centigrade. So obviously the temperature is going to be more. Outlet temperature is going to be more than 25. So I assume some Tm, which can later be checked with the actual value that you are going to get. So this is going to give me a value of Cp for the cold water as 4179. First of all, I can find out what is the total heat transfer which is taking place. That is nothing but mCph Thi minus Tho, simple heat balance. So this would be m is given as 2 kg per second times Cp is 2260 joule per kg per Kelvin, and the temperature difference is going to be 160 minus 60 Kelvin. So this value of Q would be equals 4.5 into 10 to the power 5 watts. So a simple sensible heat change, there is no phase change which is involved. So this would give me the value of Q. Now when I do this, use this value of Q and apply it for the case of cold fluid, this Q is also going to be equal to m dot C, Cp of the cold fluid multiplied by Tc out minus Tci temperature of the cold fluid at the outlet, temperature of the cold fluid at the inlet. So, since this is known to be 25, this value is known, all these values are known as well. So, the only unknown TCO can be evaluated from this as, and when you plug in the numbers, they are going to be, this we have evaluated just previously, and this would be 79C. And now you can, one thing I would like to bring to your notice over here is the outlet temperature of the engine oil is 60 degree centigrade, whereas the outlet temperature of water, the coolant water, is 79 degrees centigrade. Now, what does this tell us? Here we see that the outlet temperature of the cold fluid exceeds the outlet temperature of the hot fluid. And in our previous discussion, we have seen that if it's a case of parallel flow, the outlet temperature of the hot fluid can never exceed the outlet temperature of the hot fluid. Only if the flow is in parallel mode, only if we have parallel flow, it is possible to have outlet temperature of the cold fluid exceeding the outlet temperature of the hot fluid. I will draw those profiles once again so that we are perfectly clear in our concept about why this has to be a parallel, a counter flow situation. So, if you remember this, if this is a parallel flow, the temperature of the hot fluid, and if this is X, and the cold fluid would be something like this, both are flowing in the same direction. So, the outlet temperature of the, so this is the cold and this is the hot fluid, outlet temperature of the cold fluid cannot exceed the outlet temperature of the hot fluid. However, so this is parallel flow. However, if you have this kind of a one in which one flows, these two are flowing in counter flow fashion, then the outlet temperature of the cold fluid may exceed the outlet temperature of the hot fluid. So, this is the hot fluid, this is the cold fluid. Now, here we have the outlet temperature of the cold fluid is 79, whereas THO is 60 degree Kelvin. So, since TCO is greater than THO, this must be a case of counter flow. This information is important since we are going to use this information in finding what is going to be the delta T Lm. So, delta T Lm for this case, so we are considering this case, is going to be THI minus TCO, THI minus TCO, and THO minus TCI. So, this would be obviously be different if it's a parallel flow situation. So, that's why it's important to know whether it's counter flow or parallel flow, and this is simply going to be the ratio of these two. So, once you put in the values over here, so this is going to be 81 minus 35 by ln 81 by 35, which is 55 degree centigrade. So, your length is going to be Q by U A delta T Lm. So, this comes from the formula that Q is equal to U A delta T Lm, and your area is simply pi d times L. So, from this you get this expression of L, and when you put the values 4.5 into 10 to the power 5, the value of U is provided, pi times the diameter is also provided, and this is the value of the LMTD, and this would roughly be equal to 21 meter. So this simply tells you that the length of the double pipe heat exchanger to be provided for this operation to take place is 21 millimeter. So we have seen a couple of considerations while solving this problem. One is that very important is you need to find out whether it's parallel flow or counter flow and calculate the delta T Lm based on whether it's parallel or in counter flow. And first is all the properties are to be evaluated at the mean temperature. So I have assumed the mean temperature to be 40, and when I calculate the temperature of TCO here as about 80, then I see that I exceed my assumed mean temperature to some extent. So if I want to further refine my result, I need to use this value of the temperature and recalculate the value of CPC and do this calculation once again, and so that I get a better, a more accurate result of L. But since the value of Cp of water is not a strong function of temperature, this would give me an acceptable value. So always use the property at the average temperature. Make sure whether you have laminar flow or counter flow, and then use Q equals UA delta T Lm by choosing the right expression for delta T Lm and find out the length or anything else which is unknown. So in some cases maybe L would be known, you have to find out U. So that's the first problem which we have solved in this class. The second problem is somewhat different. So this is a shell and tube heat exchanger. Furthermore, it's 1-2 heat exchanger. So it's one shell pass and two tube passes. So if I just consider the tube, the shell side fluid is going to come in from here, flow in a tortuous path and go outside. But the tube side there is a divider over here. So the fluid enters through this, passes through the tubes, changes its direction, and then travels in this and is collected from here. So this is 1-2 heat exchanger, whereas the tube side liquid is going to be in the shell twice, whereas the shell side fluid passes only one. So it's a 1 tube heat exchanger. There are 30,000 tubes, and the wall is thin, and since the wall is thin, it means the conduction resistance can be neglected. The diameter of each tube is 25 millimeter. The steam is condensing on the outside of the tube. So here we have steam condensing on the tubes, and so there is the entire tube, the entire portion of the tube is going to be maintained at a constant temperature since it's a condensing steam. The value of H is 11,000 watt per meter square. The Q, the heat rate which is desired, the heat rate should be 2 into 10 to the power 9 watts. So that much of heat is to be removed. The cooling water rate, through the tubes, through all these tubes, is 3 into 10 to the power 4 kg per second. So if you consider water rate through each tube, so therefore through each tube it would simply be 3 into 10 to the power 4 kg per second divided by the number of tubes. The number of tubes is equal to 30,000. So therefore through each tube it's going to be 1 kg per second. The water temperature enters at 20 degree and steam on the outside condenses at 50 degree centigrade. So, the first thing that you have to find out is temperature of the TCO, the outlet temperature of the coolant liquid. That means, what is the T water outlet? The inlet is 20, what is the outlet temperature? And the second part is what is the length required which is L, let us say, per pass. So, what is the length of the tube that is to be provided per pass so as to affect this kind of a transport process? The properties which are given are for water 4179 joule kg Kelvin, the value of viscosity is provided 10 to the power minus 6 Newton second meter square. The thermal conductivity is 0.613 watt per meter Kelvin and the value of Prandtl number is 5.83. So, this is a classic problem of 1-2 heat exchanger, large number of tubes, thin, that means no conduction resistance, diameter is provided, steam is condensing. Since steam is condensing, the temperature on the outside of the tube is going to be a constant, which as mentioned is 50 degree. The value of the heat transfer coefficient is quite high on the outside. The heat to be removed is specified. The cooling water rate is provided. From the cooling water rate by dividing the cooling water rate to by the number of tubes, I can find out what is the rate of water flow through each of the tubes. I need to find out what is TCO, temperature of the cooling water at the outlet, and what is the length required per pass. The physical properties, the relevant physical properties are provided here. The first part is straightforward. The first part is what is TCO, temperature of the outlet. So, this Q, the heat to be removed is m dot C, mass flow rate of water times Cp of water times TCO minus TCI. So, that simply from a heat balance. So, therefore, TCO would be TCI plus Q dot Q by m dot C CPC. So, it is 20 plus 2 into 10 to the power 9 by 3 into 10 to the power 4, which is the mass flow rate. And remember, note that we have used the entire flow 3 into 10 to the power 4 kg per second, since we are making an overall heat balance. So, the total flow rate is to be considered, not the flow rate through each of the tubes. So, when you do that, this TCO would come out to be 36 degree centigrade. That is the first part. In order to do the second part, I am going to use this relation UA, the correction factor F times delta T log mean counter flow. This is what I was telling you, that the situation that we have over here is not pure counter flow or is not pure parallel flow. For this part, if we assume that the flow is taking place like this, so this is going to be both of them, the water and the steam, they are in the same direction, whereas the water changes its direction while coming back. So, it is not a case of pure counter flow or for a case of pure parallel flow. Therefore, this factor F is to be used, and this factor F, when multiplied by delta T log mean based on counter flow, would give me the actual temperature difference that is to be used in this formula. So, one of the tasks of this problem is to find out the value of F. But before that, I find out what is the heat transfer area, is the number of tubes, and times L pi d. So, pi d times L would be the area of one tube. It is to be multiplied by n in order to ensure that I have taken all those 30,000 tubes in my calculation, and since it is going to be twice, it is going to go through the shell twice, a factor 2 must be added in here. So, L pi d is the flow area of one tube, N L pi d is the flow area of n number of tubes, and since the tubes are going through the shell twice, that is why the factor 2 is to be included to correctly account for the heat transfer area. And the overall heat transfer coefficient is simply going to be 1 by Hi, the heat transfer coefficient on the inside, and 1 by Ho. So, that's the, so this is directly from 1 by U is 1 by Hi plus 1 by Ho, the algebraic sum of the two resistances. So, this value is provided. I need to find out what is the value of the, this value is provided to be 10 something, some value is provided for H naught as 11,000 watt per meter square. I need to find out what is this value. So, what is Hi is to be found out. In order to do this, the first thing that one needs to do is find out what is the Reynolds number based on diameter. So, Reynolds number based on diameter, to find out whether it is a laminar flow or turbulent flow, by pi d times mu. So, 4 into m dot is 1 kg per second. So, this is for flow through one tube by pi times 0.025 meters, and times mu is 855 into 10 to the power minus 6 Newton second per meter square, and the value is going to be 59,570, which is definitely a turbulent flow. So, if it is a turbulent flow, then I can simply use Dittus-Boelter equation for finding out what is Nusselt number, which is 0.023, Reynolds number based on diameter to the power 4 by 5 times Prandtl number to the power 0.4, and this Prandtl number is provided as equal to 5.83 in the statement of the problem. So, once you do all these, the Nusselt number is going to be equal to 308, and Hi would therefore be times K by D, where K is the thermal conductivity and D is the diameter. So, this Hi would turn out to be 7552 watt per meter square Kelvin. Therefore, the overall heat transfer coefficient U, as per our previous formula of 1 by Hi plus 1 by Ho, the sum of these two resistances, when you plug in the values of 1 by Hi as 1 by 7552 and 1 by Ho is 1 by 11,000, this would turn out to be 4478 watt per meter square Kelvin. So, in the formula that we have just said that Q is U A F delta T L M C F. I know what is the value of U now. The value of A is known. The area is not yet known. The value of Q is known. This part is yet to be obtained. So, the next job is find out what is the value of F. Now, if you remember, if you see your class notes, the F is expressed as a function of two dimensionless number, two dimensionless temperature differences. One is T0 minus Ti divided by T of I minus T of I. So, this capital T refers to the shell side fluid, small t refers to the tube side fluid, and when you put in the values in here, if you look at the statement of the problem, this would be equal to 36 minus 20. The temperature of the hot side is 50, minus 20. So, this is about 0.53, and the other factor which is defined as R, Ti minus T0 by T0 minus Ti, where capital T refers to the shell side fluid, small t refers to the tube side fluid. Now, if you see, for the case of steam condensing on the outside, the steam is going to condense on the tubes at a constant temperature, and it's mentioned that the steam is condensing at 50 degrees centigrade. So, therefore, the value of Ti and T0 are equal. Ti is equal to T0 equals 50 degree, which essentially gives you the value of R to be equal to 0. Now, what you need to do is you have to see what is the corresponding value of F from the figure, and from the figure you would see that where F is expressed as a function of P and R from that figure, for a value of P equals 0.53, but for a value of R to be equal to 0, this would give your value of F to be equal to 1. So, if F is equal to 1, then the length from the expression that from the expression that Q is equal to U A F delta T log mean based on counter flow, this A is simply going to be equal to A is twice pi D times L, that is the area of one pipe multiplied by the area of one pipe, considering its spending 2 times, it's a 2 pass heat exchanger. So, 2 pass, since it's a 2 tube pass heat exchanger, that's why this 2 comes in. So, the total area available for heat transfer is twice pi d L times n number of tubes. The value of U is known. So, the only unknown that we have in here is what is delta T log mean counter flow, which is T H I minus T C O. This is based on counter flow, that is why I have O over here, minus T H O minus T C I divided by ln of T H I minus T C O by T H O minus T C I. Whenever you have this problem, it is always better to draw the two temperatures. So, this is the hot side and this is the cold side, but in this specific problem the hot side temperature remains fixed at 50 degree centigrade, whereas the cold side temperature increases from 20 to about 36. So, therefore, this would be equal to 50 minus 36 for this case, minus 50 minus 20, which is the delta T over here. So, this is one delta T, this is another delta T, divided by ln of 50 minus 36 divided by 50 minus 20, which would turn out to be 21 degrees centigrade. So, the value of this is known, the value of F is equal to 1 and the value of Q is provided. So, the total length is going to be Q by U n twice pi d from this formula itself, F delta T L n based on counter flow, and when you plug in the numbers 2 into 10 to the power 9 for the case of Q, for U we have evaluated 4478, for n it is 30,000, for 2 pi, and for d it is 0.025, and the log mean temperature difference F is 1 and the log mean temperature difference is 21. So, when you calculate this, the value of L is going to be equal to 4.51 meter. So, in order to have this heat transfer process, you have to have 30,000 pipes in a 1 to shell heat exchanger, shell and tube heat exchanger, So that means one shell pass and two tube passes with steam condensing on the outside of the tubes at a temperature of 50 degree, or rather maintaining a temperature of 50 degree throughout the length of the tube, with the heat transfer coefficient specified as 11,000. Now, if first you calculate what is the Reynolds number through Reynolds number of flow through each of these tubes, that will turn out to be turbulent, and when this turbulent flow takes place through each of the tube, I can use a standard relation to find out what is the heat Nusselt number and what is HI, the heat transfer coefficient. So the overall heat transfer coefficient can then be calculated, neglecting any dirt factor or neglecting any conduction resistance. So that U part is done. The next part is to find out the right value of the temperature difference. The log mean temperature difference, since it is a mixed flow case, has to be modified by the incorporation of the factor F. So we calculate F using the standard method, and we see that the value of F turning out to be equal to 1. So next step is to find out what is the log mean temperature difference based on pure counterflow, and there we see that the shell side temperature remains constant, whereas the cooling water temperature increases from 20 to about 36. Find out what is delta T1, which is 50 minus 36, what is delta T2, which is 50 minus 20, find out the log mean temperature difference. So using the formula Q is equal to UA delta T times F times delta T Lm, you would be able to find out, when you express the area in terms of the diameter, the perimeter and the length, you would be able to find out the length to be used in this shell and tube heat exchanger. So this problem is a nice example of the use of LMTD, of the evaluation of H0, and then finally using it through a simple heat balance to find out the one unknown, in this case the length of the pipes to be used for this case. So in the next class we will see how we can design, to go into more depths of the design of shell and tube heat exchanger.